So now I should talk about Cern and an anti-miracle. I have written here LHC, but LHC is just the biggest machine and the most important machine at this institution, Cern, in Geneva, which is paid by taxpayers of many European countries. So, among which Denmark, for instance. And this Cern has just got this machine working essentially last week. We were celebrating by champagne and so that this machine had now come up to really work with 3 TeV. And now I owe you to tell TeV, that's sort of a mosquito energy. So it's very small, but it's very big on the scale of a single proton, of which we have 6 times 10 to the 23 in 1 gram. That's very, very much if you give that energy that is comparable to a mosquito. So it's an enormously big energy for that. And this is a record. And now the machine is working. And it is very great things, because the theoretical and experimental high energy physicists have been waiting and waiting for years to get the machine work. And I think somehow theoreticians have worked into more and more speculative things, because we have lacked experiments, because there has been a very long time before this machine has come up. And this is a little bit due to that we think that there is a kind of God against it. And that is a theory of Masao Ninomiya and myself. And that is what has to do with this concept of anti-miracle. We want to say that machines which produce a particle called Higgs, which is to be produced by LHC. So far, I don't think it produced any. But that will come. That will come. At least one didn't see it. One didn't see any produced Higgses at all. Also not by a smaller machine, which probably has produced about 10,000 or so. But we really don't know, because we didn't see any. So, yeah, we can put this. Yeah, so I am, this machine is called Large Hadron Collider. And large, of course, is just big, and collider means that you collide things against each other. And hadron is a somewhat screwed notation for the proton which is shooted. You should know that we are made from, we are made from protons and electrons and so on. I think you know what we are made from, but to be completely safe, yeah, you can see we are made from cells and so on, but don't forget about that. Then we are made from atoms. And here is sort of a symbolic drawing, which is in a way the picture by Niels Bohr of the atom. And inside the middle, in the middle of the atom, there is the nucleus, and that consists of protons and neutrons, so-called nucleons. And around it goes the electrons, and they are going in such orbits. But I think according to modern quantum mechanics, they are in mysterious way different places around the atom at the same time. But that we don't have to think so much about in the first go. That is quantum mechanics. Now at least you have heard the word quantum mechanics, which is what the theory which we are working on all the time. So in a way we should know that. But I think I will try to escape it in a relatively short talk. But you should have in mind that we have this mysterious theory that the creators of the theory didn't like it and complained about it. For instance, Einstein had very famous complaints. But then we have this nucleon. We have this nucleus, and it consists of these so-called nucleons, neutron and proton, which are called with a common name nucleons. And that is, so to speak, a class of particles consisting of proton and neutron. But then there is a bigger class of particles that is called hadrons. And that contains the neutrons and the protons and a lot of other particles, which I already told you. There are some called pions, there are some called, what? Yeah, that's for instance written here. Yes. There are written some names of hadrons, this class of particles. There's, as you can see, the proton, there's a neutron, there's a pi minus, pi plus, pi 0, k meson, k minus, k 0, lambda, blah, 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 blah. There are so many that we have a whole little book about them. And these particles are actually produced in collisions of, for instance, protons. Then you produce a lot of hadrons, and the proton is itself a hadron, and you also produce sometimes protons, as you can see, if you collide protons on protons. And very seldomly, you produce other particles than hadrons. And now, since I'm saying hadron is a class, I have to tell you that there is at least one particle which you should know, because I mentioned the electron going around in the atom, which is not a hadron. So electron is not a hadron, but pions, kaons, proton, neutron are hadrons. And now one calls it that one is shooting hadrons, but it is in a way a little bit strange, because this is like I would say, I am talking to mammals, because there are lots of mammals here listening, but you are all from the same type. In the same way you shoot these protons, and it is all protons in the hadron collider, but they are of course hadrons, because that's also the proton. So, but it is to make sure that it is not the electron, because one had another machine, electron-positron collider, which collided electrons, and that is another type of machine. So this is different. Anyway, so this is the hadrons. And then I should talk about this anti-miracle. And the anti-miracle, which I think is the best anti-miracle, the most mysterious happening, which could be like seeing a miracle, like seeing Jesus go on the water or so. That is that there was another hadron collider machine. And this machine was called SSC. And it doesn't really matter what this SSC was, but since I'm now mentioning it, I should say that it is meaning superconducting supercollider. So this SSC means superconducting supercollider. Superconducting supercollider. And that is because these machines use superconducting, they have the current running in superconducting, and then it was very big, and it was therefore a supercollider. In a way, it was too big, because that should have had, that should be a very big ring, 40-something kilometers, very, very big. And then there should go protons one way and other hadron proton another way, I think. And then they should go with 20 of these TV units, which is very big, because this machine we now started, that goes after plan with 7 TeV against 7 TeV. So this SSC would have been about 3 times as big in energy. So it would have been very big. And now you hear I say it would have been, because it never finished. It was stopped after a quarter of the tunnel was built. A very strange thing. I mean, it is very bad economy that you spend milliards of dollars and make a big effort to build a big machine and build a quarter of the tunnel under the earth, like a metro tunnel. And then you stop it. And all the money are in some way wasted. And it's very bad decision for Congress of United States to do. But they did it. And it is so stupid that you would almost say, this was miraculous. This shouldn't happen naturally. But it's of course a very bad thing. So probably it should be called then an anti-miracle. And now I have explained the content of this series. Now you should understand that the main point of our work, my work with Masao Ninomiya, which I shall tell you about before the talk is finished. You should hopefully have learned at least the main idea. That is that we, according to this theory, we could have predicted that this machine would have had bad luck. We didn't do it because we invented the theory many years after it had the bad luck. But we invented the theory before LHC had bad luck. But LHC has not yet had severe bad luck. It had some bad luck 1.5 years ago, and it is only starting up now. So if our theory should be fulfilled, it has better go in bad luck rather soon. So it has to be stopped rather soon. But it is not looking like it will be, because it is going extremely well with this machine. But we can of course still claim, yeah, few months we can give it and so on, and we can try to estimate how much it could have perhaps. Or we can adjust our parameters. But at least, well, what we should say is about the particle called the Higgs. And I think I must mention about the particle Higgs you must have in mind from the start. This machine, LHC and also SSC, this is looking for a particle called the Higgs Boson. And since this plays the major role in the theory of Masao and mine, I think you should notice this name of the Higgs particle, called after a Scottish physicist, Higgs. This Higgs boson is a particle one has not yet seen. So it's not seen yet. Nobody has seen it. Well, I believe somebody saw it, but nobody else believes that they have seen it. And this Higgs particle is a great thing that the LHC shall produce it. So the great LHC machine shall produce Higgs. This is in a way what it is geared to do, but it is geared to work for many years, so it won't produce Higgses so that we will see it very quickly. We have to be a bit patient before the Higgses will come out of the LHC machine, but it will come. And you should also have in mind, it is producing much more Higgses than the physicist can discover. So it will be a lot of Higgses produced which we don't see, and a few we will somehow manage to see, or rather we will only see it statistically. We have to make statistics, and we never know that what we see something that looks like a Higgs, whether it is a Higgs or not. But if we see sufficiently many times something that looks like a Higgs, then maybe it is a Higgs, or we conclude it is a Higgs. This is the kind of spirit one has to do. So now I think I should talk a little bit about this machine LHC, and at least put a picture in a way that you can say you have seen something from the Higgs. It looks a little bit dark, but you can see. And it is 150 to 150 meters under the ground. And the main thing is this tunnel here, which is a sort of metro tunnel under the earth between France and Canton Geneva, where the machine is built. And the machine is very extended. It is 27 kilometers long, and you can, for instance, show it by showing. There's nothing to see on the top of the Earth, but here is some photograph from the air of the region, and I think this is Geneva Airport lying there to give a scale of the size. But you know, this ring is 27 kilometers big. So it is a complicated landscape, and I have lived there, and it is a very nice region. And the border between Geneva or Switzerland and France is crossing around, and actually crosses this line several times. But the line, nothing is to be seen, because it is 150 to 150 meters under the ground, and it is just drawn here by red afterwards, so you know where it is. And here is again a picture of the tunnel. And if you note it very carefully, the picture I just showed you, then you will discover that on this picture there is a slightly different machine, because there was earlier a machine that was shooting with electrons which were not hadrons, and this somewhat different machine and different magnets, more weak magnets, were there, and they were used for these electrons, which for technical reasons you give them less strong magnetic fields, because if you give them strong, they lose the energy, and it is no use to do it anyway. So, but for the hadrons, you can better do it. And this is what you have. Yeah, this is not. This is the same picture, just with some put on some machines. And I will talk a little bit about one of these machines, which is called Alice, where the protons running, there are two tubes of protons running one way and the other, and they hit each other at organized places where there are very big experiments organized and so. So, this is this is basically what this machine is doing. Yeah, you can see here on the other pictures, you see some photographs before these instruments were fully developed. You have some region here with a lot of instruments to also magnets to guide and to measure the particles that come out when two protons collide head on. They split into a lot of particles, like I showed. They go mainly into hadrons, and then you look for what these hadrons are by instruments which are filling big regions. I mean, a human being is such a little small one here. It's really very big instruments. So I think like my finger or so here would be the height of a human being on this scale. And this is another instrument, CMS and so on. So you have these instruments, and now I am in I think the plan of my talk is approximately this. And I have already told you about this LHC, what sort of machine it is, more or less. And it is making records in many ways. There's a biggest cooled region down there to cool these magnets, and you have empty space where the proton run is about the best empty space in the solar system, but outside the solar system it's even more empty. It's very, very empty out there, so it's very difficult to compete with that, even for the people in LHC. I had some meeting with the Danes working there, and then one of the Danes, when I asked him, what are you doing? He said, jeg laver ingenting, which means I do nothing. But that meant he was doing the vacuum, making this empty thing. So this is the thing. If you, now the machine is working, but really, and it even worked a little bit before Christmas, but then it was stopped in Christmas, and then it is working up. And now, since last week, it's working on half the plant energy. And perhaps there is a little God effect has organized it only to go half. Maybe the God of our theory don't like to do it full speed. Well, I think this is not to be taken too seriously. But it means that one can, one has measured something with this low energy, which is not so impressive because it's essentially what one did with the previous machine. But now one is doing it proton on proton. The previous did it proton on antiproton. All particles have antiparticles. So sometimes the particle is its own antiparticle, for instance, the light particle, the photon. But the proton has an antiparticle, which is another particle than the proton. And in the foregoing machine in Cern region, one had this. But now one measured, one cannot see everything that goes in these very forward direction. You have this empty space, and you better not fill it with too many detectors, because then you stop the particle. So you have to be a little careful. There are some problems there, but they can be partly solved. But the particles that come out in a reasonably big angle, those you can see, and those you can measure. And therefore, if you want to measure how many particles there really come out, you cannot really measure them all, because you can't measure the ones coming just in forward direction or just backward when they come, so to speak, follows the protons. But you can measure the ones that come to the side, and here's some little result of this one to show that at least one has done some data, and one is now working, and they have published it and so on. So it's a great thing. Referee has accepted it. It's from, yeah, okay. And then there's this pseudo-rapidity, which is a kind of longitudinal velocity. But I don't think a logarithm of it. It is not so important to know all these logarithms. So now I have to say about what is our model, Ninomia's and mine. And I can... I think I could draw some figures about what we are doing, but I think it would be a little bit just almost painting instead of formulas. But there is one formula I would like to present as a kind of painting, because I don't think that I would even believe myself that I would make you understand it in 45 minutes. But this is the so-called Fineman path integral. And Fineman is American physicist, and he made this, which means he didn't really do it, because the truth is that it is due to one guy which is called Wenzel. And he invented, you see, this is a quantum mechanics formula. But he invented it before quantum mechanics. But, well, okay. So he, in a way, invented quantum mechanics before the other people who were more successful in getting recognized to have made the quantum formalism. But he invented this formalism, which then, and then it wasn't even Feynman, but it was actually Dirac. So, anyway, but this is just not so important historical details. And the formula I give very simplified thing because it's a bit tricky what to do. And here, this what is called past. I may call it history because I have called it history and some other transparencies. And it is really a thought history. And now I should say that this is a functional integral. And maybe there are some people for whom even an integral, ordinary way, is somewhat a murky concept. But I think that some people know what an integral is. And that is if you have some function as a function of x, then I can make an area under the function. And this area is an integral. I think some people know that. Anyway, but then if you have, if your variable x is replaced by a kind of function, you call it a functional instead, and it is more complicated. And this variable x is in a sense replaced by the history you could think about of the universe. So it's a kind of, I mean, an integral is of course a kind of sum, I hope you know, because you to get this area, you take a lot of small representative values, and then you sum the function for this, and then you, by a little normalization, you get the integral. And the integral, you know, is represented by this. This is the way you write an integral normally. But then, by analogy to that, and then to stress it's a functional, you put another d, and this is just the integral, this is the replacement for f, and this is some formula, and this e is 2,71828, the Neper logarithm, and this I is the very important thing which I want to discuss is square root of -1, and I think that most of you know that this doesn't exist, that square root of -1 doesn't exist because you can't, the square of all normal real numbers is positive and -1 is negative and therefore cannot have a square root. But I think also most of you anyway know that you formally play with such square root of -1, and then you say, now we are playing with complex numbers. And if you have this I, which is a square root of -1 in your formula, then of course there's no doubt that your formula is somehow written with complex numbers, because otherwise it is meaningless. So, of course you have complex numbers in your formula. But then it is very mysterious. Normal people assume that this so-called action, this is called the action, this quantity here. This action is supposed to be real. But now you see, how strange to assume this is real when the formula is anyway going to involve complex very strongly. Therefore, you might, I mean, this was hoped to be an aesthetical, which means very weak, sort of artistic point, that this is not very reasonable, but rather a strong assumption to say that this action is real. But that is what all the physicists normally do. So they assume the action in the Feynman path integral due to Dirac and Wenzel is a real number, but not complex. But Ninomir and I, we assume it to be complex. This is, I want to say, this is a little bit suggestive by the story here. But it's very little suggested. But anyway, whether it's suggested or not, we assume that it is complex. And then we get some effects out of this, And I think you might understand if you can see this algebra. Yeah. What does it mean that it is complex? I don't think I should go into this algebra so much, but this is something like that you have an I times an so-called imaginary part. And if this imaginary part is multiplied with this I is multiplied by this I times I is -1, so you get e to the minus this I. And if you know the exponential, when you have something, and this h bar, which is Planck constant, that's supposedly very small, because that is so small that in daily life we consider it almost going to 0, because then we get classical physics instead of quantum physics. But anyway, I don't think I shall go much more into that, except to say that the bigger this SI is, the smaller is this, and therefore the less important. So the most important in the whole thing will be when the SI is the smallest, which means most negative. And that leads to a suggestion for a sort of formula for the will of God. Because, let me say that this will of God is this formula here. This was the imaginary part of the action. And I have not really told you what action is, because I've just mentioned this Dirac formalism in which you can use the action. But so indirectly I told, but very indirectly. And then I said that what is important must be histories for which this function of a history. So you should think of a functional of a history. You should think that I could write a formula which I avoid writing for you, but which would say whenever I have a history, I can calculate a number. Or rather, I can calculate two numbers, a real and an imaginary part. And then I could say, now the true history of the universe, selected by God in quotation mark, is the one that gives the smallest number for this one. So now you would have a rule according to which you would know how to start the universe in order to play off the history that would give the minimal value. It's a little bit analogous to that you say that this God who leads the universe, he is like a director of a company, and he tries on his computer to evaluate different scenarios for how things can develop through all history, and then he finds out some of them will give deficits, some will give bigger deficits, some will give perhaps a negative deficit, and then he chooses that history of the company if he can, but he can. He's almost like a god. He's here. Then he chooses that history that gives the best benefit, which means the most negative deficit. And this SI is supposed to be like the deficit, so he tries to make the SI so small as possible by adjusting the history of the universe. This is a kind of will of God, because he really is very similar to a human will, because it is like wanting to get a certain achievement, namely this minimal deficit, this minimal SI. And that means then that all events that would cause a lot of contribution to the SI, which is positive, he would hate them and avoid them for any price. So if there is some contributions that are very big to this SI, he will hate it and will try to avoid it. And now the suggestion is that Higgs particles are of this kind. So he hates the Higgs particle. But the Higgs particle is the thing one has built the LHC to produce. So conclusion would be that this God in quotation mark, in order to minimize his analog to the deficit, SI, would do all he can to avoid having the LHC run so that it produces many Higgses. He will try to stop it before it has produced too many Higgses. Oh, a few Higgses, okay, 500,000, but nothing important. Not very many. And that was what he did in the case of the SSC, which I mentioned. You remember the SSC was the superconducting supercollider. I didn't tell it was in Texas, but it was actually built in Texas, and it was built 1/4 of the tunnel or so, and then it was stopped by the Congress. So this got in quotation mark. What would he have done? He would have seen that this was a very bad machine because it would produce a lot of Higgses. So stop it. And then he did arrange things in a clever way, whatever he could find that could help it. Maybe he called on Gorbachev or somebody so that he could make the Soviet Union collapse, and competing machines in the Soviet Union get hopeless for several years, and then we made it a little bit more expensive, a few milliards more expensive, and then the Congress gave up and stopped the machine. Because then competition was not so good anymore, and it had even got more expensive. It was still great science, but, most of the Congress didn't even hear my talk now, so they might not really know. So that would be the problem. And then it was stopped. And this was, in a way, an anti-miracle. It was then confirmation or support of our theory. So we would consider its support. Now it turns out that LHC should also be killed now, of course, because it will also produce Higgses. And 1.5 years ago, there was a kind of bad luck for it, because there was a happening. One had almost started it one had started it, but the particles were only running with energies corresponding to the foregoing machine. I think you might, maybe it's good to have in mind that this machine is this Large Hadron Collider. Here I have a sort of symbolic drawing of the circle again, which is at 27 kilometers. But then you have to put in the protons, and you should put them in already with some speed, because if they don't have high speed when they come in, they are much more difficult to control, and they will not function in the way the machine is adjusted. It's adjusted only when they have high speed already. So you take the foregoing machine, which is called SPS, you speed them up to the highest one you could do on the Cern region in Geneva, and then you pump them over from there, and then you should speed them up again. But first you have to make them run, and that one managed to do, but then happened bad accident, and there are superconducting conductors, and they have zero resistance, but they don't quite have zero resistance. Where you glue them together, there is a little resistance, and if this resistance is a little bit too big, it's very, very small, nano, it's extremely small, but it's there, and you put big currents through, then it gets heated up, and when it's superconducting, it's no longer superconducting when it gets heated, and then something happens. And then something happened just a few weeks before. One was to celebrate that now machine was working. And my collaborator Nino Mia and all the great people from the different countries were called there to to celebrate and so on. But then a few weeks before, there was some heating there, and there came an explosion, and there was a big light from current there, and the helium, which should cool the machine, and which is minus 271 degree, which means 2 Kelvin, was boiled, of course, and there was a big explosion. And even if the security machineries worked, it couldn't take it all, and there was a spoiling of a bit of the tunnel, and one had to repair, and then one found out that one had not checked well enough all the other places around the 27, and then at the end, when one finally had gone, there was gone more than 1 year to return. So it was delayed more than 1 year. So this God, in quotation mark, he postponed it for 1 year. And then he managed to make it half size, so not so many Higgses as if at full size, full speed, 7 TeV plus 7 TeV, but only 3.5 plus 3.5. And that's the situation. And now it started again. But if our theory should be right, it should better stop soon. Okay, maybe we can give it a few months or so, especially if it runs with this lower energy and lower intensity and so on, lower luminosity. Yeah, here we see some of the news. Here is the guilty part. It is, yeah, you can't see very much, but it is some part here which is shown. That was the guilty part. So, right, I have a feeling I should almost conclude.
5 minutes.
What?
5 minutes.
Ah, okay. Yeah. So, yeah, this was a plan. It's not so crucial. I have already talked about it, and I have given an idea of the thing, and I have given an idea about the Fineman. So I should probably just more or less conclude that we have we have here. Sorry. Yes. I have talked about this LHC machine at Cern that started, and I have told that one shoots there 3,5 of this tera electron volt. I could, to be sure, I could remind or mention that this tera electron volt, so that you know it, 1 tera electron volt is 10 to the 12 electron volt, which means 1 million electron volt. I think you call it trillion in some English, but I hate to use that because in Danish it is billion, which means milliard in English. So it's very confusing to talk about this if you don't know what language you're talking. So, but anyway, a million electron volt. And an electron volt is the energy that one elementary charge gets when it goes through 1 volt. So if electron goes through the net on 220 volt, it gets 220 electron volts. So, so this is the tera electron volt, and you put on each of the proton for the moment 3.5 of those the one way and 3.5 the other, and the total collision gets then 7 because it's 3.5 plus 3.5. And then I mentioned some instrument, Alice, for which the Niels Bohr Institute is very much involved. It's involved both in ALICE and in Atlas. But in ALICE, ALICE instrument is actually one that is especially gained when you shoot also, not with protons, but with whole nuclei, lead nuclei or so, against lead nuclei or gold nucleus, against gold nucleus and so on. So then this ALICE should be very good at measuring a lot of particles, and that may be that it is therefore rather good at measuring how many particles you have and so on, and that's one of the first things one gets out of this instrument. If I'm allowed to measure one of the things myself, there is something called KNO scaling, which is a law for how the distribution of the number of particles develop when you go up in energy. And this is called after Kobe, Nielsen, and Olesen. Nielsen is me, and Olesen is... But unfortunately, in a way, already the little machine, which was called SPS, which was the last machine to put it in, found out that Kobe, Nielsen, Olesen scaling was not right. So it's already falsified. Yeah, so it's already falsified. And now the successful working is falsifying mine and Ninumir's model about that these machines shall have bad luck. So this is another model that has bad luck. And this is a bad sign that it is working. But it is a good sign that it was delayed 1 year, as I already mentioned. And there are a couple of other good signs. Well, the one good sign, which was the main anti-miracle, that was this machine called SSC, Superconducting Supercollider, which had the bad luck of being closed completely by the Congress before it worked at all. And this was in 1993. And it had something like 21 kilometers of tunnel. And then, yeah, then there was this half. And then John Ellis wrote, but I think it was other people who found out, that in a way, if these Higgses were hated so much as they should be by the God that governs the world, in quotation mark, then the cosmic ray, which is that particles come in from the universe and hit the atmosphere and produces particles. It should not produce Higgses, because it is not good, because then you produce much more Higgses than LHC and all these machines together. So it's very bad, and it is very bad. But of course, nobody knows how difficult it would be to switch off these cosmic rays of a very high energy that can produce Higgses, because they have to have even more high energy than what you produce them in the LHC, because you are hitting the atmosphere where you have atoms which are at rest approximately. So you need much more energy. You don't have, in the LHC you collide like this. Two collide on each other, head-on collision. But if you come cosmic ray to hit a nucleus of nitrogen or oxygen in the atmosphere, it comes along and the other is at rest. So it has to go with much bigger, not speed so much, just a little bit bigger speed, because they all go with speed of light. But it has to go with bigger energy to cause same effect. But then, very interestingly, it is cosmic ray that is so high in energy that it would produce Higgses. There's nothing to do about that. It is true. But there is a funny kink. There is a kink in the sense that when you come to an energy where you begin to produce the Higgses, then the curve describing how much cosmic radiation there comes goes much deeper down. So it is as if it falls down when you come to the place. So it is as if there is an effect that these ones which could produce Higgs gets cut away much quicker as a function of the energy. So when you go up in energy, they disappear rather quickly. So they are much less than there would have been by a simple extrapolation. So in some way, they were removed. So you see a slight support for the idea. And this is and this is called the knee, because the curve comes to look like a leg with a knee. Here you have the normal, and then it goes down. Right. And that is funny that this is very close to this place. And this is then some evidences for it. There's also the little problem that there is already a machine in Chicago that produces Higgses, but nobody saw them because they're difficult to see. So they produce Higgses and probably have produced 5,000 or whatever. But they probably produced them, but really we don't know. But then we have to say, but we put a parameter in our theory, and it is only when it is enough many we get this effect. So maybe if we have less than 500,000, it is not a problem. But at least we should not put the parameter so that we lose our best miracle, which was the SSC machine, because then we lose all evidence for our theory. and that would, of course, be very bad. So we must live with that. So, but now you can listen and hear, and if you don't hear within some months that accident actually happened or so, then it's not so good for our theory. But of course, theories should be falsifiable. So really, they are not usually falsifiable, such theories, because you can play around with the parameters. But more and more, you have to give it crutches and help it and so on, and say, we put the parameter up and so on. And finally, it is effectively falsified. And this one is going to be effectively falsified probably at the end of the year or before. I mean, so that is the sort of situation. And and then of course I can tell that, of course you can now expect that in a way I would be nastily hoping something bad to happen, because it's nice to have your theory be successful. But you see, it is also nice to have a working LHC, because then you get wonderful theories that can test other theories of yours, which is nice to do. For instance, I have a bound state which I would like to get found. And if it doesn't work, it's not easy to find any bound state with it. So it's very important to get it work also. So I'm more balanced. Yes. Whereas perhaps to some extent, colleagues might be less balanced, because it's very sad. They have no consolation if it goes wrong. Yeah. And in a similar way, with respect to the Higgs being found, some people are thinking that it is very dull if you just find the Higgs and not much more new stuff. But that's, in a way, what some of the theories I believe most would give. So that would be a little victory and also be consolating. Whereas otherwise, this finding the Higgs and nothing else, that is sometimes called the Rosner-Bjorken nightmare, because Rosner and Bjorken find that it's almost a nightmare, because one hopes to find new theories to be true. And I must tell in the last second that one of the theories one can hope to be true, that is superstring theory, for which I claim to be a father, together with Nambu and Susskind. And but I'm perhaps a bad father, because I don't trust it very much. But therefore it could be true anyway. And this is what is hoped, or is possible, that LHC may find it before it finds the Higgs. And if the superstring theory is true, probably one should find 5 Higgses and not just one. So there is something very interesting, and one should find supersymmetric partners. So it will also be either supported or perhaps falsified, but you can always give it crutches. So it's not so catastrophic either. But